we presented the idea of the state operator map, and we found that we could match states and operators where all the states built out of the vacuum with oscillators. But we are starting to wonder what sort of operator would be related to states with momentum. So which operator can I insert in the plane that will give me a state with momentum on the cylinder? Now, see, roughly speaking, if you want to create a state of momentum P from the vacuum, I can do something like that. Almost by definition. Where X is the zero mode of the scalar field. I'm going to put hats here and there today because otherwise there will be infinite confusion between P, the eigenvalue, and P, the operator. So, roughly speaking, we would like to find an operator with a property that, as I send this operator to the very path on the cylinder, perhaps by normalizing it by something, I will get P. Okay. The same way as yesterday, we used tricks like this. So this factor was used to convert this into the Z. And this expression was the reason we said that A1 minus 1 inserted acting on the path ground state would match the Zx inserted at the origin in the plane. So, roughly speaking, we want an operator with a property that it behaves like this. It should be an operator which starts like this. And then perhaps there's other stuff, which either is killed by sending tau to minus infinity or is killed by acting on the vacuum. The simplest thing I can try to do is to define an operator. Because this is a zero mode of the scalar field, I can try to define an operator like this. So roughly speaking, if I have not really defined this operator, but if I could define it reasonably, when act on the vacuum, the zero mode would transform the vacuum to P. The positive modes of X would kill the vacuum. And the negative modes would be killed by sending tau to minus infinity. So can we make sense of this operator? Now, if you're looking at things like powers of X, we know we can define them by things like point splitting, or normal ordering. So roughly a way to define this operator might be to just expand it in powers of P and define carefully each power of X with subtractions. There is an alternative way which is often useful for calculations, which is just to insert this expression in the path integral and see what comes out. in previous lectures, I only worked on the cylinder and sort of left calculations on the plane for homework. But here I want to do both because they are both instructive in different ways. So suppose I have some path integral. It could be on the plane, it could be on some other manifold. I don't care. I have my free boson action. And I want to insert an operator like that. Because this is an exponential, essentially what I'm doing is I'm adding something else to the action. I'm adding IP x evaluated at some point. Actually, I can insert even several of these operators. And possibly write that as an integral on my manifold. Notice this I is not the same as this I. I'm sorry. Square root of minus 1. Okay. Mm-hmm.
I assume when you're multiplying that operator, like you're trying to take the expectation value of it, but do you have issues in the fact that the x doesn't commute with the action?
It's a path integral. Those are numbers. They're not operators anymore. So that's one advantage of doing things with path integral. Everything you do inside a path integral is just manipulations of numbers. Operators come about if you start slicing your path integral and get in the states. So now, finally, you might think that perhaps the delta functions are going to give me trouble. And you can try to regularize this problem a little bit. Put some smoother functions here, depending on some cutoff, with the understanding that at the end we'll take our functions back to delta functions. Okay. So at this point, this is a very nice object. It's a nice Gaussian path integral. It has a quadratic part in x and a linear part. Right? So you know how to do Gaussian integrals. Right. So we know that this integral is going to give us something like so the inverse A here was sort of the kinetic term of the scalar field. So 1 over A is the propagator for the scalar field. So here you get something like this. Is that clear? So now is this expression going to work when I take my limit back to delta functions. So, I mean, the mixed terms where I'm looking at different operators will surely be fine. This will become just g of z, I, zj. No problem there. The diagonal terms will be a bit troublesome because they give me something like g of zi, zi, except that the two-point function of the scalar field is a logarithmic singularity, and the points coincide. So I have some troublesome terms that look like this. So in order to regularize these troublesome terms, I had to add a counter term. So I'm going to say that the real way to define this operator is not just to insert this linear term, but also a constant term. Sorry. As usual, I'm not being precise with factors of 10, factors of pi, factors of 2, factors of -1. But these are all expressions you can find around on references, textbook notes. So this correction removes the short distance singularity of the operator. So this is now a perfectly finite expression as a sen f to delta functions. So that's the way we define these operators in the context of a path integral. Now, this definition has some entertaining consequence because, as you can guess, this regulator depends on my coordinate system. So if I change my coordinates, if I do the usual holomorphic change of coordinate, this will change. And so the definition of my operator will change by an overall rescaling. Now here I'm doing everything in conformal gauge. So implicitly I have a flat metric and working with holomorphic coordinates. If you prefer to work with generic metric and think in terms of wild transformations, here you're going to put the metric distance along between the 2 points.
So the logarithm here appears as the Green's function in 2D, right?
Yes.
But that's for some boundary conditions, which is for open boundary conditions, right?
No.
When your Green's function depends on the boundary condition.
This logarithm is the singularity of the Green function where the 2 points coincide.
Okay.
So it doesn't matter what's going on far away. Indeed, if I'm exactly on the plane, this is exactly the Green function. And it cancels out these diagonal terms completely. So this means that if you change your coordinate, and then you do the proper wild transformation to go back to the flat metric, your regulator changes by something like this. Sorry, supposed to be busy. Okay, this is a simple calculation. So the funny thing is that when we're redefining, regularizing things like the stress tensor, which are polynomial in the fields, the changes in the renormalization ended up in giving us extra additive terms when we change coordinates. But here, because everything is exponentiated, the correction when you change coordinates is also exponentiated. In other words, the operator defined with some coordinate system and the one defined in some other coordinate system differ by a pretty amusing power of the Jacobian. So you should compare this with the transformation law of, say, dx. So this operator behaves like it has some funny power or some indices. To say is that this operator has an anomalous dimension, meaning under the scaling of your local coordinate system, it gets multiplied by a funny factor. So it's entertaining that even if you are in a free field theory, these exponential operators manage to have an anomalous dimension.
Why is it to the p squared, not just to the p? Doesn't the 2 in that squared cancel with the 2? Ah, the p squared there.
Comes here, and 2 terms comes
Okay.
here.
Yeah.
Because we're regularizing the diagonal parts of that. And the fact these vertex operators have anomalous dimensions is actually the reason that you can have fun things like bosonization, which you might encounter at some point, I hope, which relate theories of look kind of trivial, like a free boson, to theories which have, like the Ising model, which have interesting operators with non-trivial anomalous dimensions. So you can actually describe a whole lot of non-trivial two-dimensional conformal field theories as free bosons or variations of free bosons. Now, okay, so this was all done with the path integral. Let's see what we do on the cylinder instead. Now, on the cylinder, we need to give a meaning to an expression like this, where this x now is an operator, is this sum of x, p, a, n's, a minus n's, sums of operators which don't commute. Actually, sorry, before we go there, let's get the answer. Here. So after let's see what is the correlation function on the plane of a bunch of these vertex operators. So the gain function is just a log. This counter term cancels out all the unwanted, all the diagonal terms. So to get is sort of a product over pairs of operators, or something like this. Let me just make sure that I got the things. So, okay. I'm trying to remember if I got it right or if there was a true here. I think this was it. Yes. That's a kind of a neat expression. And of course, with a bit more patience, one can compute more complicated things with whatever insertions of x you want, still by doing the same sort of Gaussian integral. Now let's try to do things on the cylinder.
Right there, the average, the index I goes in the set coordinate or in the field. So there.
Sorry.
Right. But what does it mean set I minus set j at the others?
Right.
Okay.
Now,
If I calculate the vacuum expectation value of only one of these, I would get 0 or something more.
no. On the plane, you can always have implicitly some momentum going to infinity. So here I was. So I think, yeah, the 1-point function is actually 1. When we look at the sphere, indeed will. So let me start by looking at some toy model. Suppose I'm given this sort of exponent, and I want to normal order it, meaning I want to really separate the modes that kill the vacuum on one side, and the ones that kill the vacuum on the other side, for ease of calculations, if you want. So I claim that this formula holds. I hope that my alphas and my a's are distinguishable. So alphas are just numbers. Okay. On the other hand, the a's are operators. Okay. So I claim that this is true. There are various ways you can try to prove this. You can just expand the left-hand side and expand the right-hand side and play around with combinatorics. You can try to write a differential equation in alpha 1. Okay. See, for example, let's look at just the first non-trivial part of the calculation. On one side, I might have 1/2 of alpha 1, A1 plus alpha minus 1, A minus 1 squared. Okay. So when you expand it, you'll find 1/2 alpha 1, A1 squared, 1/2 alpha minus 1, A minus 1 squared, which are going to come from these exponents. And you also find alpha 1, alpha minus 1 times A1, A minus 1 plus A minus 1, A1. Then you can use your commutation relations to write it in an ordered way. Sorry, it was a half here. And then a number. So you should recognize the expansion on the right-hand side, the second order in alphas. Okay. This generalizes in an obvious fashion. To this. I hope this is clear. Okay, so now let's try to make sense of an expression like that in terms of operators. Again, let me regularize it exactly the way I did it there. So let me try to make sense of an operator like this. Just to smoothen it out a little bit. So these alphas are going to be roughly the Fourier coefficients of this F. Let's decompose X into the zero mode, the momentum, and the parts that contain the positive and negative modes. So, for example, if you remember the expressions I wrote in the second lecture, I guess not like that. Okay, so when I normal order it, I'm going to, well, I had to deal with the, I'll deal with this later. Okay, so I get roughly something like that. And now I can apply this sort of formula. And try to figure out how does this look like. How does this contribution look like? This is the only thing I really had to worry about, because after I regularize this, these guys and these guys will just behave perfectly well if I make my f back into delta function. So if you just evaluate this, you get precisely so to regularize this, I need to evaluate what happens if I consider this. Okay. Then this guy is going to be integrated against f, and this guy is going to be integrated against f. But let me just look at that for a moment. So I get something like e to the minus the square over 2, sum over positive n, 1 over n, e to the n s prime minus s, as compass conjugate, times the normal order of exponentials. this is exactly the same log as we had there. So this gives me, this is nothing else than p squared over 2 log of 1 minus e to the s minus s prime, s prime minus s, sorry, squared. So this is exactly the kind of term that can be regulated by a log of s minus s prime squared. So if I regulate this operator exactly the same way as I regulated on the other board, I can get to a final answer. So this is what's called a normal ordered exponential. And it's usually sort of fun to play around with these things, see what happens if you multiply them, commute them, and so on. But usually it's more laborious to do things like this than to do them with path integrals. But now that I have this definition, it becomes easy to show. The desired result. So this verifies that the Vertex operators on the plane with momentum p are related by the state operator map to the states of momentum p on the cylinder. So this will be invaluable in, as I mentioned yesterday, this will be invaluable in computing string theory scattering amplitudes, because it means that whenever I have these sort of tubes that come in and want to join some more complicated picture, I can always do a wild transformation and smoothen out the tube. At the price of putting a Vertex operator there. So if you do that to all the tubes, you reduce your problem of computing the scattering amplitude, the problem of computing the correlation function on the sphere of a bunch of these Vertex operators. Okay. And then you use that formula. You get your answer. Now, as I mentioned, the sphere, let's see the simplest possible example of calculation which might involve a sphere. Let me start with the cylinder. With the usual flat metric. And let me do a wild transformation, which blows up on both ends of the cylinder, as opposed to the wild transformation which we did to go to the plane, which blew up only at one end of the cylinder. So I'm going to divide this by this Weyl factor. So this is going to collapse both ends of the cylinder to something smooth. If I use the usual exponential map, I can write my metric like that. Which is the metric on the sphere in stereographic coordinates. The smooth round metric. So I claim that this Weyl transformation relates the cylinder to the sphere. Okay. So in this coordinate system, so this coordinate system is sort of like a plane. It's like a projection of the sphere onto a plane. So roughly z equal to 0 at the North Pole, and z goes to infinity at the South Pole. On the other hand, if you define a second coordinate, z to the minus s, z tilde will be 0 at the South Pole, and z will be infinity at the North Pole. So this is a standard way to describe the sphere as a complex manifold. You take two patches, each looks like a plane, and then you glue them together. An equation like that. So in each of the two patches, if you want, you can put a conformal, you can put a flat metric by Weyl transformation. And then there is a Weyl rescaling when you go from one to the other. So this means that when you do correlation functions on the sphere, they will usually look very similar to correlation functions on the plane. The only extra information that there is when you work with the sphere is that you get to specify operators placed at infinity in the plane. So here the precise correspondence is that if I put some state v1 in the past and v2 in the future, on the sphere I get an insertion of the corresponding operators. Related by the state operator map. Locally, the correspondence between the cylinder and the sphere near the South Pole or near the North Pole is the same as the one we had with the plane. So these are literally the same operators that you would have put on the plane. But now you get one at the North Pole and one at the South Pole. So at the level of vertex operators, there is not very much to say more than what we already said. The only possible remark is that on the cylinder, there was an interesting constraint on the momenta of these vertex operators. So if I try to study some correlation function with some momentum in the past, a bunch of vertex operators, and then some momentum in the future, a bunch of vertex operators, and some momentum in the past. Because of the conservation of momentum, because the translations of the scalar fields are a symmetry. This is a big delta function. Okay. Now, when you go to the sphere, both this state and this state will give you possibly vertex operators. Okay. Corresponding statement of the sphere is that if you're on the sphere, you have a product of then this gives you a big delta function. And then you get your product of pi minus cj to the pi dot pj. So if you want to think about the sphere and work on the plane, the prescription is that putting an operator at infinity on the sphere is the same as putting at some finite distance and then sending it to infinity, except you need to account for the coordinate transformation between infinity and 0. So you get something like z to the twice. It's called the scaling dimension of the operator. The scaling dimension of the operator is simply the sort of power of the Jacobian that appears when you change coordinates. By now we've seen several examples of this formula. Sorry, I never mentioned the conformal dimension yet. Well, we didn't need. Now I'm going to start mentioning it. So, for example, so there are these two numbers, delta and delta bar. Sometimes they're also denoted as h and h bar. Okay. So they tell you how the operator changes when you change coordinates. If you for example, the first derivative of x over there might have delta equal to 1, delta bar equal to 0. The Vertex operator over there had both delta and delta bar equal to p squared over 2. So the meaning of delta is that delta plus delta bar is the scaling dimension. If I scale my space-time, the operator gets multiplied by the change in the scale to the delta plus delta bar. On the other hand, delta minus delta bar control the behavior of the operator under rotations. Suppose I do z goes to e to the I alpha z. I get opposite factors from z and z bar. So this is the spin of the operator. Mm-hmm. Also, if you have a state operator map, so if you have some state related to some operator, because, let me see if I have the right picture. It's up there. Because time translations become scale transformations in the plane, and translations in space become rotations in the plane. The spin is the same as the momentum, space momentum. And the scaling dimension of the operator is the same as the energy of the state, up to the Casimir energy. Or more precisely, delta goes to L0 at L0 eigenvalue, and delta bar goes to the L0 bar eigenvalue. So, for example, you know that the momentum had eigenvalues p squared over 2, both for L0 and L0 bar. And we saw that the Vertex operator had delta, well, and delta bar both equal to p squared over 2. Similarly, del x was related to a minus 1 acting on the vacuum. And a minus 1 raises L naught by 1. We're actually not going to be using this formula. I just mentioned it for reference. I just keep my operators away from the North Pole anyway, from the South Pole. But right, when you start studying conformal field theory, I hope these things will come out useful. So, right, so as I was mentioning, right, and the way to understand why do I get the delta function here, if you want, I'm studying this free boson on the sphere. I'm doing a path integral for the free boson on the sphere. In particular, there is an integral over the zero mode of this scalar field. And this imposes current conservation. You know, if you have e to the ix times something, and that something is non-zero, if you integrate over x, you get 0. Mm-hmm.
I'm just trying to see if I understand. Are you claiming that the transformation properties of V, like under conformal transformation, you need to give me delta and delta bar, and that specifies completely how it changes under conformal transformation?
If it is what's called a primary, in a sense, this is the definition of a class of operators, which are called primaries. Some other operators might have more complicated transformations.
So the ones that we're dealing with, they're all primaries.
That's right. The stress tensor already is different from this. The stress tensor had an extra term proportional to C over 12, and the Schwarzschild derivative of this vector z tilde. And there is another example of something that transforms not quite like that, which is the Gauss number current.
How do I go about finding out what my scaling dimensions are?
Well, you check how you define your operator in different coordinate systems, and you compare the two definitions.
For a particular example of you're dealing with derivatives of, say, for a minus 1, you have derivatives of x.
That's right. Well, so x itself, in a sense, right, so x itself does not transform when you change your coordinates. Del x is its first derivative, so it just transforms by the chain rule. Composite operators need regularization, so have the potential to transform in more interesting ways, because the regulator might not transform well under your, might not be invariant under your coordinate transformations. Now, I stated everything here in terms of coordinate transformations. There is an alternative language, which is to think in terms of wild rescalings. So, but if you want to sort of use the power of complex analysis, these are the sort of formula which come out to be very useful. Now, I think in one of the tutorials today, I think you're going to study something called OPE, operator product expansion, which is a way to just use complex analysis as much as possible instead of using complicated operator identities. So you can get actually a lot of these results right away without going to a path integral, without going to commutation relations of operators. Okay, looks like we still have 10 minutes. So for the free scalar on the sphere, I told you pretty much all that you need to know. you have your correlation functions. You can add some extra derivatives of x, whatever you want. You make sure that you have momentum conservation, and then you do your calculations on the plane. For the ghosts systems, things are also quite straightforward, just for one little subtlety. So as I mentioned in the previous lectures, the ghost number current is anomalous, which means when you do a wild transformation, it shifts. The charge, the definition of charge shifts, of ghost number charge shifts. Another way to say it is that there is the conservation law for the ghost number current. It's a bit damaged. It's not 0. It's something like 3 or maybe 3/2. I don't remember. Times the curvature of your space. So as you can see, on a sphere, it's definitely going to be damaged. On the plane, it's going to be fine. So when you look at correlation functions of ghosts on your sphere, an expression that you were thought would give 0 because of current conservation, right, will give you non-zero, or vice versa. More precisely, on the cylinder, on the plane, or in a situation in which the ghost number current was conserved, I would essentially expect that if I have the same number of B's and C's, I get non-zero. If I have more B's than C's, or more C's than B's, I'll have 0. It's because it would be exactly like having because of this condition, what actually happens is that on the sphere, you get things that are non-zero if you have 3 more C's than B's. Now, this might sound somewhat confusing, but if we just start from calculations we understood on the cylinder and then go to the sphere, everything will be, I hope, clear. So if you remember, on the cylinder, we went through a certain set of interesting states for the system of ghosts. There was a ground state, and another ground state. And then there was another state we found interesting because it was BRT invariant. So, and we said that the ground state can be written as C1 G. That the ground state can be written as C0, C1 G, sorry, 0. And then by symmetry, you can imagine there is another state third state that can be interesting. Let me call it 0 tilde. Okay. So this state was annihilated by B minus 1, B0, B1, etc. It was annihilated by C2, C3, etc. Now this guy is now annihilated by C1 because C1 squared is 0. It's not annihilated by B minus 1. So B0, B1, etc., kill G, C0, C1, C2, etc., kill G. And so on. This other G prime was killed by B1, B2, etc. This was killed by C0, C1, C2. And finally, this guy is killed by B minus B2, B3, and so on. And this is killed by C minus 1, C0, C1, etc. And we computed the Gauss numbers of these states, and the result was kind of neat and symmetric. This is the Gauss number minus 3/2, minus 1/2, 1/2, 3/2. And finally, you can convince yourself that this sort of expression is the only expression that can be non-zero. So if you want states to have a non-zero net product, you essentially want them to be killed by complementary sets of operators. So because 0 is killed by these ones, the dual state will have to be killed by B minus 2, B minus 3, B minus 4, B minus 5, and by C1, C0, C minus 1, etc., which are the dual conditions to this state. So this is the sort of the inner product which is non-zero. Also, it makes sense from the point of view of Gauss number. Gauss number is conserved on the cylinder. Let's write explicit what. There's now a convenient way to write this. Which is this one. Now, why is this important? I'm going to make a claim, and then we're going to check it. I'm claiming that the state operator map relates 0 to the insertion of the identity operator. So if you want to put no operators on the plane, you've got to put that vacuum in the past. And one way to verify it is to go back to the 2-point function, which we computed. Well, we computed, which I told you can be readily computed at some point. And perhaps some of you computed. Okay. Now, the exponential map, if you look at the conformal dimensions of C and B, so C actually has dimension -1. And B has dimension 2. It kind of makes sense because the dimension of the stress tensor is also 2. It's, dx, things like that. And you want the BRST symmetry relates T and B. Another way to think about it is C was a vector field, and B was a true form, but not true form, symmetric tensor with 2 lowercase indices. So if you do your exponential map, C on the plane is going to be e to the s C on the cylinder, and B on the plane is going to be e to the -s 2s C on the cylinder. And so you see that this implies that 0 tilde CZ dz 0 is 1 over z minus z prime. And this is the 2-point function of the Gauss system on the plane. So you can check it with the definition of the Gauss action. You do the path integral on the Gauss on the plane, and you get this answer. Very simple. Okay, sorry, I'll have a couple more minutes. So this shows you, these and similar calculations can show you, convince you, hopefully, that this is the state that corresponds to put nothing. And the same is true for putting nothing at the south pole of the sphere. So this shows you that when you work on the sphere, you got to have 3 C's to get a non-zero result. Starting from this, it's easy to show that the correlation function which is the same as the correlation function of C on the sphere. Essentially, you look at this, you expand them in modes, and you pick up all the possible combinations of C minus 1, C0, C1. There are 6 of them, and they're the 6 terms of this product. Okay. This is all the all the information about ghosts that we'll actually ever need to compute scattering amplitudes. The fact that the triple function of C's, of 3 C's on the sphere, is that. Sorry, I have this bad habit. I behave like the all antelomorphic ghosts do not exist. It's not a very good habit. What I really mean is that I need to have 3 ghosts, 3 C's, and 3 C bars to have something on 0 on the sphere. I'm sorry. Okay. So this was really supposed to be something like that. Sorry. Okay, and actually, I can't resist computing a triple function, a scattering amplitude of 3 tachyons. We have all that we needed, so let's just do it. It will take 1 minute. So I want to study a process in which 1 tachyon decays to 2 tachyons. So 1 tachyon is coming to the past in some momentum mode 1, and is going out to the future into 2 tachyons. Let me just use a convention in which all momenta are ingoing. So I have P1 going this way, P2 going in here, and P3 going in here. Now, is this kinematically possible? Sure. This is a tachyon. The momenta are space-like. And there is no problem having 3 space-like momenta which add to 0. Okay. I can draw them on the board. So this amplitude has a chance to be non-zero. So how do we compute it? First, so remember the tachyon state looked like that. This was the Q closed state in the cohomology with p squared equal to 2. I want to use the state operator map to convert this state into an insertion. So I'm going to map this picture to this picture. So I'm going to insert. And I need to use the state operator map for this. And this becomes simply that. C bar e to the I p dot x. More explicitly, this is really p mu x mu. Okay. So here I have a sphere with 3 operator insertions: C, C bar e to the I P1 X, evaluated at Z1, say, let me call this point Z1, Z2, Z3. I have C bar to the I P2 X inserted as Z2, and C bar e to the I P3 X inserted as Z3. Okay, so let's compute it. We know that the C's are going to give us Z1 minus Z2 squared, Z2 minus Z3 squared, Z1 minus Z3 squared. I know that the moment Vertex operators are going to give me that expression up there. Where is it? Well, under the blackboard. Sorry. Yes. So I get Z1 minus Z2 to the 2 P1 dot P2, Z1 minus Z3 to the 2 P1 dot P3, Z2 minus Z3 to the 2 P2 dot P3. Okay? Times conservation of the momentum. Now, momentum conservation means that, say, P1 squared, which is equal to 2, is also equal to minus P2 minus P3 squared, which is equal to 2 plus 2 plus 2 P2 dot P3, which means this is minus 2, this is minus 2, this is minus 2. So 2 minus 2, 2 minus 2, 2 minus 2. The answer is just 1. Well, it's a delta function of the momentum. Okay. So there is no dependence left on where did I place these points. You might wonder why. The point is that actually you can completely gauge fix the position of the points, meaning you can always file a wild transformation which maps this same picture, to this for whatever position of the points you want. A way to understand it is that you can always do a coordinate transformation. Which is holomorphic, well defined everywhere, and maps the sphere to itself and moves these points wherever you want. So if we did our gauge fixing properly, the answer better not depend on our gauge fixing. And so you see that the ghosts and the matter fields are cooperating together exactly to kill the dependence on the gauge fixing. So the choice of position of these points, Z1, Z2, Z3, was part of my gauge fixing. The answer should be independent of the gauge fixing. So it better cancel out. And it does. OK, so from this, we just learned something. I don't know if it's this or not, that this process happens. The tachyon can decay into two tachyons. Now you can try to, there's not much fun to have with processes involving only 3 particles, because usually decays are not kinematically very interesting. For example, if you want to have 2 tachyons going to 1 tachyon in Lorentzian signature, it doesn't work very well. Sorry, 2 gravitons going to 1 graviton, maybe it's not working very well. But you could, in principle, look at other processes like that. Is it possible to have I guess it should be possible to have a tachyon scattering of a graviton. Can you do it on shell? Yes. Right. I could have a graviton scatter off a tachyon at rest. So perhaps as an exercise, try to do that. try to see what happens if you scatter a graviton off. If you, well, not really scatter off. Try to see if you can compute this process in string theory. No. It's really part of the scalar field's correlation function. So the correlation function of the scalar field in the sphere has a delta function.